Okay, so let's continue applying Gauss's law to find the electric field. Let's do the example of the infinitely large plane with surface charge density sigma, uniform surface charge density sigma, and we want to find the electric field at some distance, let's call it d, from the plane, above the plane, let's say. So Gauss's law says that the integral of the electric field over a closed surface is equal to the charge that's inside that closed surface divided by epsilon naught, and we want to apply this. So here's our let's make a drawing of our let's see here. Here's our infinitely large surface, and we're looking at it. Well, I guess that would be called edge on, so that the plane is here, and if we look at it from above here, then we'll see the actual plane, right? So we're sort of in the plane, in the infinite plane, and we want to now construct a closed surface on which to integrate the electric field, but our closed surface has to involve regions where the electric field is everywhere the same, so as to be able to pull the electric field out of the integral. Okay, so let's say we want the electric field at a distance d. So we are at a distance d here, and other places where the electric field must have the same magnitude, clearly by symmetry, given the way the charge is distributed, involves other distances from the plane of the same length. So here is a line over which the electric field must have the same value. But that's of course a line. We need a surface. So if we look at this from above, right? So if this is our infinite plane, this is sort of a section of the infinite plane, and we're looking at it from above, then the distance d, this line here, looks to us like this from above, but we're looking at it from up here. We need to construct a two-dimensional region. So it could be maybe a rectangle. Okay, so we are at a distance d, and that rectangle could have a width and two sides, w and l, let's say. Okay, and then so this is the distance d as well. But that's true at a distance d below the plane. The electric field must have the same value, so we can imagine constructing a rectangle. Right? It's not the only two-dimensional surface that's useful to us in this case, but now so we have a rectangle below as well that has the same dimension. So if we make another drawing of this where we don't look at it edge on, then it looks something like this. So we basically have constructed a box because we need a closed surface that looks like this. So the top, so let's draw the surface where the charge lives in red. So that's the part of the red plane that is inside the box. Let's see if I'm doing this okay. If I come back across here, we should come across the front. Maybe I'll just, goodness, see if this works. I'm going to come back around here. I'll be in the front of the box, and this is at the same height as that, and this side is below, and this is W, this is L, this is W, and this is L, and it looks something like that. Okay, so we have two top surface and bottom surface, but we have to close all of that off with the sides. So we end up with a box because Gauss's law applies to closed surfaces. So although it's true that the electric field on the sides might vary with distance, so it's not everywhere the same, it's also true that just like in the example of the infinitely long line of charge, we won't get any contribution to the electric flux on the sides here because the electric field, which we'll draw in red, on this surface is pointing this way above. So these are electric field lines. The electric field is pointing that way above and this way below. Right? The electric field is normal to the surface, and so on the sides, we could imagine that the electric field above the plane is larger, so that our arrows can be a little larger. But they don't produce any flux because they don't go through the sides, so when we do the dot product with dA, we get 0 through all the sides. Draw a field there. Let's draw some dAs. So here the dA is pointing straight up. The same is true on the bottom. dA is pointing straight down. Right here it's pointing this way. So again, we see that we don't get any contribution to this integral on the sides. Of course, we could do it right here. The dAs would be pointing out toward us. Here, the dAs are pointing that way. And so we get 0 contribution to the dot product there. So now we can do the calculation. So what does this side reduce to? Well, we just said that we get a contribution on the top rectangle. What does that look like? It's the electric field is everywhere a constant, so we just get the magnitude of the electric field times the area of this rectangle, which is W times L, but the same is true on the bottom side. So we get E times W times L there, and that's it for the left-hand side. We get no contributions on the 4 other sides. And the right-hand side is, well, all we have to do is look inside the box and see how much charge there is. So here's where the charge is inside the box, inside the closed surface. How much charge is there? So let's point out the amount of charge there in blue here. So the amount of charge Q, so we would call that Q enclosed because it's the Q inside the box, that's just the charge density, which is capital sigma, times the area. What's that area? Well, it's the same area as the top rectangle and the bottom rectangle, and so it's just W times L. That's the amount of charge enclosed, and so the right-hand side looks like sigma WL over epsilon naught, and so the left-hand side is 2 electric field magnitude times the area of our surface times sigma WL over epsilon naught, and that gives us the magnitude of the electric field at a height d. Notice that d doesn't come into this, so it doesn't matter what your height is. It's true of any height. It's just sigma over 2 epsilon naught in magnitude, and we can turn that into a vector as we did before by associating a unit vector that we already know must be normal, must be n hat because the electric field is normal to the red plane. And that's something that we use in constructing the closed surface. And so we end up in just one line being able to solve something that took us many integrals to do by brute force.